Welcome to the 20th lecture video for Physics 4C. This is our first lecture treating physical systems in a fully quantum mechanical way. As this involves mathematically sophisticated and conceptually challenging approaches, we will take our time this week and next week, fully introducing and applying the analytical approach of the wave mechanics formulation of quantum mechanics. We will necessarily have to limit full solutions to the simplest systems that we can actually solve for in this lower division class, but we will still explore the meanings and usefulness of a couple more wave function solutions. So, in this lecture, we start with an introduction to wave mechanics, in which we no longer rely on classical models. The setup of particle in a box, that is an artificial setup in which a particle is localized in a region of space with infinite potential walls, gives us an environment in which we can derive the predictions of quantum mechanics. We then introduce the non-relativistic time-dependent Schrödinger. By the way, when not using umlaut, Schrödinger's name is spelled with OE. Schrödinger Equation. First by introducing the momentum and energy operators, and then writing down a statement relating to the mechanical energy of a system. Then, using the Schrödinger equation, we will fully solve the particle in a box system, fully justifying some of the choices made in the earlier attempt. We ended this video with a short discussion of wave functions, particularly the energy eigenfunctions that are solutions to the time-independent Schrödinger equation. We have much more to discuss in wave mechanics, and we will bring them in one at a time in the upcoming lecture videos this week and next week. So last week and the week slightly before, we were introducing early ideas of quantum mechanics. And I guess if you read this introduction, I'll say, I hope you feel like you understand quantum mechanics, because now it's going to get difficult. So this is the first week where we are actually going to give a fully quantum mechanical treatment to physical systems. So up until now, everything we've been doing was semi-classical, as in we had some experimental results we were trying to explain: black body radiation, photoelectric effect, and the stability of a hydrogen atom. And the way all of this analysis proceeded was we are using classical mechanics. We were using what we felt familiar with, except for maybe one key step where you put in that quantum mechanical assumption, right? And now what we are going to do is we are going to see a fully quantum mechanical approach to a physical system, so that you are kind of looking at things from the other end. Because here's the thing: classical mechanics, Newtonian physics that you are familiar with, that is not the correct description of the world. And you cannot derive the correct law of nature from the incorrect law of nature. It doesn't work that way. You can maybe guess at the correct law of nature from whatever you get from Newtonian mechanics. But quantum mechanics, even though it's more complicated, more difficult to understand, it is actually more fundamental. So you can derive classical mechanics from quantum mechanics, but it doesn't work the other way. So with chapter 7, with what we are doing today, this week today is, well, how do we describe something just starting from quantum mechanics? And it's going to be a very challenging thing. So we are only going to ever deal with the simplest possible pictures. But let me give you some footing that you have from last week. So I guess I can write them down as quantum mechanical assumptions. These were the quantum mechanical leaps that each of those semi-classical approaches were taking. And what I can tell you is that these assumptions themselves are right. You just have to put them in the correct context. So what I want to do now, take a bit of time to go through, is an analysis of the simplest possible quantum mechanical system one could possibly imagine. And that's what's called particle in a box. There are different ways to visualize it, all of which will be wrong. Let's see. Let me first draw a picture, and then I will try to explain how you might liken it to a particular system. So for this particle in a box picture, this is what you would imagine. So you have a particle, something like this, that has mass and something. So at a minimum, it has mass. We are not dealing with the photons. We are dealing with a particle that has mass. And it's in a, I guess when we say box, really it's a quote-unquote box. Because I guess it could be a literal box. But if you are actually trying to build an experiment, it wouldn't be a literal box. But so it's in a box in the sense that if you have a particle, you may imagine in having some potential energy as a function of position, right? Yes? Let's say where in the middle of the box here, let's say this is where your potential energy would be 0. And as this particle moves around, its potential energy doesn't change, almost like this ball rolling around in this, on this table. But at some point, it encounters a barrier, as if there's a sudden potential jump if this particle tries to go from here to here. And in the idealized picture, you would say this potential goes to infinity once the particle tries to go beyond this point. For, I don't know, sake of convenience, let's call this point x equals 0. So if the particle were ever to be found in a negative x position, then it would have an infinite potential energy, and that's not possible. So we would say, okay, the particle is never found here. Okay? And particle is bounded here, and if it's going to be a box, you have to have boundary at the other end too. So once again, what I'm plotting is kind of a potential energy of this particle as a function of position. As it's moving here, its potential energy isn't changing. We are saying that's equal to potential energy reference level, 0. But let's say at some point here, let me call that x equals L. Some length L, after the particle travels some length L. So up to this point, potential energy is 0. But if the particle goes one step more, then its potential energy once again will approach infinity. Okay? So we call this particle in a box because that's sort of the visualization of what it represents. Like imagine motion of a particle that's here. Let's say it has some kinetic energy. It would, let's say, start by going to the left. When it encounters this wall, then there's, however much kinetic energy it has, it's not going to be enough to climb this potential wall. So it'll get bounced back. And then here, the same thing will happen. It'll get bounced back, so it'll bounce back and forth. You can kind of imagine this, this ball that's bouncing back and forth between this, bouncing back and, I guess it's not elastic collision, so it's not working out well. But you can imagine this kind of bouncing back and forth. And in the idealization where this brass ring is indestructible, no matter how much kinetic energy this has, when it collides, it'll bounce back. But this is where I'm saying it's kind of difficult to visualize this correctly because so you might look at this and say, oh, but it's only a tiny step. Couldn't it just jump over like this? Which is actually not wrong. So maybe more realistic experimental scenario you should think of is you should think of this as being a charged particle. And imagine that it's moving in a region with a 0 electric field, except if it crosses over some boundary here, electric field goes to infinity. So that the particle would barely penetrate this region and then be repelled back by the electric field that's pointing out. And the same thing happens at this wall. That's how you would build this wall. You would actually build it with electric fields, so that it's actually elastic collision and all that stuff. Okay? So this is the simplest quantum mechanical system we can imagine. It's the simplest because well, the interaction in this range is simple. Well, there is no interaction. There is no force. Like with that electric field example, in this region, there is no electric field. This is behaving like a free particle that's just free to move around. No potential energy, no force, just whatever quantum mechanical thing it's doing, right? And somehow the setup is made so that this particle cannot spread out infinitely. It's confined within this region. Okay? So with this setup in mind, we can ask these key questions. Let me split this question into two parts. A is, what is smallest possible energy of M? Let me have you think about that for a little bit. And the second question, once we answer this, it would be, let me write it down now. What are allowed energies of M? Yeah. So this question actually contains this question in it. I felt this would be easier to handle for now. Yeah. So we have a mass. I'm going to have to be careful not to break the speaker. We have a mass that's confined to be within some region of space. It's a bit of an odd question to ask. What is the smallest possible energy of this mass? Intuitively, what is your answer? Zero? At rest, zero kinetic energy, right? That is the classical answer. That so it's zero potential energy. Let's say it's at rest. So zero kinetic energy, zero energy. Now, so yeah, that's your intuition. Your intuition is built on classical physics. So let's just double check if that intuition is correct quantum mechanically. So zero kinetic energy, what else does that imply? Like any other physical quantities that zero kinetic energy is necessarily associated with? Zero momentum, right? Zero kinetic energy means not moving, so zero momentum. So this is where we check it with a quantum mechanical, I guess maybe I shouldn't say assumptions. I don't have any better words though. Well, I'll just keep it as assumptions. I almost want to call it postulate, but it's not universally accepted. So let's check against this. So maybe you don't have anything wrong with it having zero kinetic energy, zero frequency. What's wrong with it? Maybe there's nothing wrong with it. But this is where you'd come across a problem with. You are saying it has zero momentum. So that means it has an arbitrarily long wavelength. Infinity always causes problem with the people. So let's just say, we can make the momentum arbitrarily close to zero, which would mean wavelength being arbitrarily long. On this picture, let me just sketch a wavelength that is arbitrarily long. I guess I can start from here. So starting from here, this is an example of wavelength that's arbitrarily long. Like, I'm just drawing one cycle of one long wavelength. And so this portion should be troublesome to you. What's wrong with this portion of the wave that I've drawn? Yeah, okay. We already started with saying this should be inside the box. So once you are outside the box, then without knowing any other, laws of quantum mechanics, just for this to be self-consistent with what we have described, we have to enforce that whatever the wave represents this has to be zero outside, so that we can say outside, no particle. same thing on this end, 0 out here. So that outside, no particle. Then here, now you have a discontinuity. And so whatever this wave is that I'm drawing, you don't have an intuition for it yet. I will just say this much. When you have a discontinuity, that's unless you specifically know why it's discontinuous, it's going to be problematic. And in fact, we'll see later that this wave that we are describing can never be discontinuous. Sort of like, I guess it's hard to build up an intuitive sense of this, but it's like saying, let's say this represents some kind of a wave on a string. And if the string is ever discontinuous, then means your string broke. You no longer have a medium for your wave to be on. So as a matter of just making sure whatever mathematical description we are building is sane, it's behaving reasonably, which is always the case in a physical system, at least that's our assumption. We have to enforce that this wave has to be continuous. That if this wave is going to go to 0 outside, it has to go to 0 in a way it's continuous. Okay? Now, once you have a shape like this is no longer one wavelength. It's not, by which I mean you cannot describe it with a single sine wave. You have this steep slope here that's going to involve really short wavelengths to explain. So our goal is this. What is the smallest momentum that's consistent with the existence of this particle? And that's the same question as what is the wavelength that is consistent, longest wavelength, that is consistent with this potential setup. So we imagine drawing different wavelengths. And really the longest wavelength I can fit here is a wave that looks like this. Right? So if I'm looking for smallest possible energy of m, so I'm looking for longest possible wavelength. And what is my longest wavelength lambda in terms of L? 2L? 2L? Yes? This is half of a wave, and half is equal to L. So the wavelength is equal to 2L. Does this make intuitive sense? That this is the only description of this particle possible that's consistent with this quantum mechanical assumption. Yeah. And so this is kind of an intuitive approach to particle in a box. I haven't introduced the Schrödinger equation. I haven't told you anything about this wave other than imposing some reasonable conditions on it. The conditions that, if our world is, so. And this is actually enough a piece of information for us to answer this question. What is the smallest possible energy of M? Well, so energy that must be, in this case, just all kinetic energy, because we are dealing with the non-relativistic mechanics and zero potential energy, so all of your energy is now kinetic energy. Do you know any expressions for kinetic energy that might be useful here? What is the expression for non-relativistic kinetic energy? Someone other than Gauge. I know you're looking around to see if someone else will answer. Everyone here forgot how to express non-relativistic kinetic? Well, 1/2 mv squared, that's a good start. Now, there's a bit of a problem here because I have no idea what the velocity of the particle is. Like v is not in the list here. So I would like to re-express this in terms of something that's here. What is here that we can use? Yeah, momentum, because you know from non-relativistic mechanics, momentum is mv. So the v, you can write as p over m. And when you go through algebra, this kinetic energy will get this expression. P momentum squared over 2m. Yeah? And this is the very last step. So we have information on lambda. We know how to relate it to momentum through this expression here. Once we know the momentum, then we can figure out the kinetic energy. So the energy is, let me factor out 1 over 2m times the momentum, h over lambda, or h over 2l squared, h over 2l squared, or, let me just expand it out, simplify it all. Then you get h squared over 2 times 4, 8 ml squared. And this is what your textbook, or somebody will, sorry, I haven't read your book. I don't know if you noticed it. I don't read the textbook all that carefully. I'm leaving it for you guys to read it carefully and let me know if anything's wrong in it. So this is what textbooks should be calling ground state energy. Ground state meaning the state with the lowest amount of energy. Ground state energy of particle in a box. This is the lowest possible energy for a particle that's confined within a box. Now you can see that as the box gets larger, as the allowed longest wavelength becomes longer and longer, as L increases, this energy goes down as well. But if you want to make the box smaller, that necessarily involves the smallest possible energy becoming larger and larger and larger. Yeah. So yeah, that's it. This derivation, it really only took this quantum mechanical idea. It didn't take anything else. It didn't take the Schrödinger equation, or later today we are going to actually rederive this using Schrödinger equation, and we'll just get to the exact same answer. And that's why I want to offer this as one of the stepping, like terraformer, a ground that you can step on and trust on for everything you do in quantum mechanics, that this will never be wrong. There will be situations where you can't quite apply this. Maybe you're dealing with something that doesn't have a fixed wavelength. Deal with that later. But if you have a wavelength, like here, then you can describe it. This is a good way of describing it. Okay? Okay, so the second question is an extension of this. What are the allowed energies of M? It's the kind of a same question as if you were asking what are the possible wavelengths lambda. Let me just draw a few to give you an idea. I don't want to use blue. I guess I'll just use this color. So I drew one wavelength, one shape of a wave that would fit with the condition that it has to come to 0 here and 0 here. Let me draw another wave that could fit under that condition. So 0 here, say, oops, comes to 0 again, and then 0 here again. That's just one full sine wave. Sorry, I'm not drawing it very well. Let me redraw it. So something like this. All right. Let's see. Or I can start with a 0 here. I feel like I skipped something. Did I skip something that's possible? Yeah, what did I skip? Yeah. So I should. There's one where I fit in 1/2, 2 halves, and then 3 halves. One that kind of looks like this, right? Does this begin to seem familiar with something you have seen before? What have you seen before that kind of looks like this, shows you this kind of pattern that you saw in physics 4a? Okay, maybe not. All right, let me. So I want you to have the correct mental image. The phrase I was looking for is a standing wave.
but maybe you don't remember. Maybe your instructor never covered the standing waves, which would be terrible, but it is possible. Especially if you took physics not at Peralta, then actually different schools cover these topics in different orders. So it's perfectly possible that your instructor did nothing wrong and they never covered the standing waves. Because here we do it in physics 4a. So this is kind of an image you need to have. So high tension, no damping, let's see, oscillate, slow motion. So I happen to have a lot of numbers memorized for this, so let me just put that in. So I happen to know 0.43 is a frequency that gives, lowest frequency that gives you a standing wave. I use this simulation enough that I have that number memorized, or should. All right. Oh wait, I want it normal speed. So, wait, didn't I show you guys a standing wave? I feel like I have. When did I do that?
I think we went over backwards waves again.
Oh, okay, yeah. Yeah, okay, so you guys should have heard of standing wave from me. So this is one. So this is the longest wavelength that you have seen. The next longest or next shorter wavelength that you have seen, that's where you double the frequency. So this should actually 0.85. So this is the next standing wave. And let me lower the amplitude so that it's clearer. So what you see with here is that this looks like a sinusoidal shape with a zero, more or less zero here, and zero at that end. Okay, so that's the next one. And you can keep going because this simulation you can go however high you want. So next one is 1.2, I guess 2.8 or something. Let me do 7. That's probably closer. So that's the next one. That's the one I deliberately missed. At least that's my claim. So that's the one with the 2 nodes. And as you see this, you will begin to see a pattern. With each allowed frequency or each allowed wavelength, what the pattern you should see is that the number of nodes increase by 1. So the next one that's allowed, there should be around 1.7. So around 1.7. So we had 2 nodes before, right? So with this one, we should see 3 nodes. And 3 in-between nodes, I mean. So node here, here, and here. Okay? And I can keep going, but I hope by now everyone here now has a mental image of this standing wave. So that's actually what we are describing. Because here, in trying to have whatever shape of the wave it has, have a definite wavelength, meaning it has to look sinusoidal, either it has to look like a sine, a portion of sine, then the condition that we are imposing is the same condition we are imposing for standing wave, that it must have a node here, and it must have a node here, and in between, it must be continuous. Okay? So it might take a while to kind of guess a correct expression for wavelength. In the interest of time, let me guess it for you. So it's going to be a kind of a fraction of this 2L. That's the longest one. And the fraction will take the form of 2L divided by integer n. Okay? That seems about right? Where this integer n would be, I guess, the number of nodes in between plus 1. So for the longest wavelength, the green one, this n is 1. The next one, this one that I drew, second, n would be 2. So your wavelength is L. The next one would be n equals 3. So that it's, the L is the 3/2 of lambda. But all of this kind of coming back, especially those of you who took physics 4a and here, and you kind of remember the standing waves in a like tube experiment and all that. Good. So yeah, so these are the possible wavelengths, which gives. So this gives possible momentum. So this gives possible momentum of h over lambda. So it'd be n times h divided by 2L. NH divided by 2L. That's the possible allowed momentum. I might even put a subscript n to emphasize that the only possible values are where you have an integer n equals 1, 2, 3, 4, and so on. And well, with this, imagine plugging in here, you get the possible allowed energies of this particle in a box. And that would be, so allowed energies would be this momentum squared divided by 2m, or n squared h squared divided by 2m times 2l squared. So the same 8ml squared. So 8ml squared. This is remarkably similar to the lowest ground state energy. The only difference is that you have n squared. So this is a special case where n was equal to 1. Good. So this is actually one of the key results. This is actually when I do assign your homework for chapter 7, some set of questions will be simply using this formula. And you can derive this formula using the whole Schrödinger equation and wave mechanic tools, or you can kind of guess at it intuitively, sort of starting from what is reasonable for the wave to behave, and just this one quantum mechanical assumption, and the rest of the mechanics that you already know. So I want you to, this is not the order your textbook does it, but I want you to start out with this so that quantum mechanics is hard. It's the full mathematical treatment of it is difficult. It's all about solving differential equations, and I will tell you that this is the only case where we are actually going to solve differential equations. The other two, the simple harmonic oscillator and the Coulomb potential, I'm just going to give you the solutions. I'm not actually going to solve those differential equations because they're too difficult. So the quantum mechanics, wave mechanics is mathematically difficult. It's no cakewalk. It's an upper division content to actually treat them with a full on. And it's also conceptually difficult. We are going to deal with maybe some aspects of it today, but interpretation of quantum mechanics is an active area of research. There's a mainstream interpretation called the Copenhagen interpretation, and that's what we are required to teach you in class by law, even whether we believe it or not. But reasonable physicists disagree on what is the true quantum mechanical picture. So in special relativity, I told you there are no paradoxes in special relativity, only misunderstandings. I will not say that with the quantum mechanics because there are, retired professors who won't be convinced that any one interpretation explains everything that they think are weird about quantum mechanics. So quantum mechanics is conceptually difficult. So with all those difficulties heading our way, I wanted to give you something that's a firm, kind of easy to grasp, and nothing here is wrong. Everything here is correct. Maybe it's a bit of a simplified picture, but everything here is correct. So with that, I guess I should properly introduce Schrödinger equation so that we actually have the tools to work through wave mechanics. Let me spell Schrödinger two different ways. So one is the way you've seen me spell here, O with the umlaut on top. If you know some German, then you know what that is. If you don't, and you just want to be able to type it with the English characters only, this is how you should spell it. Schrödinger. The wrong one is where you just say O and don't put anything else there. That's wrong. If you don't want to put umlaut, it should be OE. So Schrödinger equation. This is the first wave equation that was, I guess, discovered, because this is kind of a fundamental law of nature, ignoring relativity. This is the first wave equation that was discovered that describes the quantum mechanical, quantum mechanical nature of nature. The goal here is this. We want to have we want to have a differential equation that's going to be our equation of motion. Do you guys remember way back when we were doing simple harmonic oscillator? Way back in physics 4A, when you're doing simple harmonic oscillator, that somebody should have derived something called the equation of motion. Something like the 2 double time derivative position is equal to minus k over mx, like coming from Hooke's law. Yes. Or when you're doing waves, somebody should have derived this equation of motion for like a piece of string for describing wave on a string. Something like if I have a piece of string, so let's say I'm describing y position of the piece of string, then the equation that would be derived is that partial time derivative of that y position, or this piece of the string, actually double partial derivative, is equal to, I'll do it correctly, v squared, and then double partial derivative of the position with respect to x, the horizontal position. Like, remember seeing that? Yes, sorry, I usually write x here, but I kind of did it the wrong order. So this is an example of wave equation, which describes wave on a string, right? And you have seen a similar wave equation that describes electromagnetic wave, right? Now, those waves are a bit special. So electromagnetic waves, they would be associated with something that's moving at speed of light, something that's massless according to special relativity, right? So Schrodinger's goal was to come up with a wave equation, come up with an equation of motion for whatever wave this wavelength is representing, except that it would be applicable to something that has mass, not massless, because if it's massless, then it's relativistic. It's non-relativistic. So he was trying to come up with an equation like this, except that it would apply to something that has mass. Yeah? So, it's a very abstract exercise. So let me just shortcut some of this whole. I call it derivation, but once again, it's not derivation. The Schrödinger equation is the fundamental law. You cannot derive the fundamental from something that's not fundamental. You can only guess at the fundamental from the things that are not fundamental. So he was trying to guess at this equation, kind of using the classical wave equation as a guide. Classical wave equation is a differential equation. So the goal we have here is a differential equation, which a wave, like the wave here. So here, this y as a function of position and time. This is my wave. This wave would be required to obey. So if we are saying that whatever kind of wave all these are, if we are saying this ought to be described by some kind of a wave function, traditionally represented with the letter psi, as a function of position and time. And at this point, it's very mysterious what this function actually represents. With wave on a string, I can actually tell you, this y, it represents the height of this piece of string. But here, I don't actually have a piece of string. So this particle, it doesn't have to be charged. So I'm not necessarily describing electric fields either. So whatever this wave is made up of, at the moment it's very vague. We are not sure what this wave is made out of. You can kind of imagine back when people were doing whole is light wave or particle debate, and when they with the experiments decided light is a wave, you can kind of imagine wave of what? Before they discovered the Maxwell's equations, they didn't know it was an electromagnetic wave. It's the kind of same deal here. It's a wave of something. We don't know what that is, except that we can describe by a function of position and time. So with Schrödinger equation, let's say we have some kind of wave function psi as a function of position and time. This somehow represents the particle we are trying to describe. Then the next challenge is, all right, we have a wave function. How do we measure its properties? So you have only two guides in measuring the property of this wave function is two of these quantum mechanical assumptions. That when you measure its momentum, it should be related to its wavelength. When you measure its energy, it should be related to its frequency. So this is where last time I simply guessed at these operators. So let me just write down the operator and I'll kind of explain how they are reasonable. So these two are the operators for momentum and energy. So the momentum operator, let me represent it with this. This head is just a notation saying this is not a mere number. It's representing some kind of mathematical operation. And the operation it represents, I'm going to write it slightly differently than how I wrote it last time. Last time I wrote it as h over I. This time I'm going to write it as minus IH. It's the same thing, right? Minus IH is h over I. Okay? And times this derivative with respect to position. That's what I mean. This is an operator. It's not a function. It's not a number. This only takes on a meaning once you operate on something with this. Okay? So this is a momentum operator, and this is the energy operator. H bar. Forgot the bar. IH bar, partial derivative of time. You could take this as, you could take this as actually the fundamental assumption that these are the, this is my starting place. And this is one of the things that are kind of confusing, not confusing, what's the right adjective here? Challenging about quantum mechanics. In special relativity, you had a clear set of two postulates, the principle of relativity and the constancy of speed of light, or universal speed limit. Everything you did, you started from there. Quantum mechanics has a traumatic childhood. It has multiple different beginning points. So you could use these two as beginning point and then get everything else from that. Or you could use these two as the beginning point and then arrive at these two. So we're not going to privilege one over the other. And that's why I didn't want to say these are postulates, because I can actually say, well, these are my postulates. And then I'm going to get at that other thing. So let me just show self-consistency. Yeah?
I have a question. So energy, when we define it, it's kind of, it's like work, right? And it's force over.
Work is a change of energy.
I see. But isn't it kind of strange that energy, we're taking the time derivative?
Yes.
It makes more sense to be taking, like,
Well,
X.
let me show you how this is consistent with what we are saying here. Yeah? So I want to have a kind of a prototype wave function, which is going to be a very, very simple wave function. It's so simple that we can use that wave function to see if these are correct operators for momentum and energy. And what's the simplest wave you can imagine? Sine wave. Okay, you are telling me the shape. So if it has a fixed wavelength, it is going to be sinusoidal. By simplest, this is what I mean. So this wave that you saw here, this standing wave, is this the simplest possible wave? What's unsimple about this, Kevin? Yeah, this is, well, there's multiple nodes, and actually there's one more thing. Like, what is the standing wave result of?
It's a superposition
Superposition of two waves propagating in the opposite directions. So really, if you want the simplest possible wave, you should have a no end here. so that any wave that's reflecting back is gone. So you have really this. This is kind of closer to the simplest possible wave. Anybody remember a name for this?
Traveling wave.
You could call it traveling wave, I guess, if you're in one dimensions. We live in three-dimensional world. This one happens to be transverse, but it could also be longitudinal. Do people remember the phrase plane wave? Yeah, it's a, let's say, take it in opposite to spherical wave. So plane wave is where you go far enough away that the wave front varies, or the, this height of the waving thing changes only in one direction, and in any other direction, nothing changes. So plane wave is the simplest possible form of wave, and this is the mathematical expression for plane wave. Plane wave. This psi. Let me use the complex exponential notation because there's no way around it. This plane wave has some kind of amplitude, and it is a function of position and time in this form. Complex exponential of kx minus omega t. Right? This is plane wave, or it's the mathematical representation of a plane wave. And depending on what this A is, it could be plane wave of many different things. It could be this plane wave. It could be electromagnetic plane wave. And what we are claiming now is that this could be a representation of the matter plane wave. Something that is mass, if it can be represented the wave function, then this is a possible representation of that. And now we want, given this wave function, we want to kind of propose a procedure for measuring its properties, its momentum and its energy. I guess it's kinetic energy. Because the way plane wave is going, it's not interacting with anything, so it probably doesn't have any potential energy. So let's just say we only have its kinetic energy. So the procedure for measuring its momentum and energy would be this. This is where it would be so much easier for me to explain if you guys have taken linear algebra and you knew what eigenvalue meant. How many here have heard the word eigenvalue? Some of you, but not enough of you. So let me just write it down what the phrase would mean. So I have a mathematical operator. I can act with this on a function. That's a valid thing to do. So I can do this calculation. Given a function here, I can act on it with my, let me do color coding. I can act on it with my operator, right? Now, in general, you are not going to get some simple expression coming out the other end. This can be kind of, in general, this doesn't necessarily have anything to do with the psi, right? But there might be special cases where after you apply this operation, the function you get actually is related to psi. In fact, it might even be related this way. It might even be related as psi times a simple number, a scalar. Let me give it a letter p. Under the special circumstances where we have this, we say this is the momentum of psi. Now, if you don't have this special circumstance, then what that would mean is this psi doesn't have a definite momentum. It's a combination of different states, like the standing wave that has two different momentum combining in it. So it doesn't have one momentum. It has multiple different momenta. Okay? So this is our proposed mathematical procedure for measuring property of this wave function. We have an operator, and if we have this special wave function, where after acting with operator, if we get the same function back, multiplied by some number, then this some number is the measurement of that property. Good? All right? So once again, I'm not driving any of this. I'm just giving you something that at least going to be self-consistent. So that would be the procedure for measuring momentum. The procedure for measuring energy would be exactly the same. You are acting with the energy operator on the wave function psi, and hopefully this psi, if this psi is a state with a definite energy, then we would get the same function back, except multiplied by some number, and this number would be the measurement of the energy of psi. And here's why we are trying to describe a plane wave. It's because plane wave is so simple. This is a state that has a definite momentum and definite energy. That's why we are doing this with the plane wave, because if we try to do this with a standing wave, we wouldn't get momentum, because it's a standing wave is not a momentum eigenstate. Standing wave does not have one definite momentum. It has two definite momenta. So let me do this simple calculation with this plane wave. So I have momentum operator acting on psi, and I only have exponentials here. So it's actually a pretty simple calculus step to go through. So I have, all right. So so I'm going to be doing this. So minus I h bar times this derivative. The derivative is not going to change anything here really. So let me start out with that. I'm going to still have a exponential of I kx minus omega t. That's the derivative of the outside, the unchanged outside. And using the chain rule, I have to take the derivative of this with respect to x. So I get a factor of ik from the derivative. So let me put that here. So ik, that's the derivative. Let me finish with this minus I h bar. Minus I h bar. So this is the result of applying this momentum operator on the wave function. So what we get, this is the wave function psi, which is good. We are kind of looking for that. So this is a momentum eigenstate. It's a state of definite momentum. And this number here is the measurement of that momentum. Or let me simplify it. This is, so simplifying this, minus I times I is just 1. So h bar k. Is h bar k equal to h over lambda? Yes, this is where you have to remember the simple definitions. H bar is defined as h over 2 pi. And k, wave number, is defined as 2 pi over lambda. So, h bar times k is h over lambda. So this is h over lambda. So the description that I gave is consistent with that quantum mechanical assumption. So at least this operator for momentum is consistent with that expression. So right now, that's all I'm shooting for, self-consistency. I don't want to be telling you A is equal to B, and then tell you B is equal to C, and then tell you A is not equal to C. I want to be able to say A is equal to C. Let me do the energy. So for the energy, it's going to be the same thing. So so I have this wave function. When I take the derivative, the time derivative, nothing's going to change. It's an exponential. So I will get the same exponential back, a times exponential of I kx minus omega t. So that's the derivative of the outside. Derivative of the inside, I kx minus omega t. So I'm going to get a factor of minus I omega. Right? So let me pull that out here, minus I omega. So that's the time derivative in the energy operator. I still have I h bar. I h bar. So when you multiply this out, I times minus I, that's 1 again. You have h bar omega. is h bar omega same as this expression here, h times frequency? Yes, this is where you should remember that omega is defined as 2 pi times frequency. So h bar times omega is, 2 pi's cancel out, h times f. Good. So, if I told you that, this is our starting place, this is at least consistent with what we have discovered in people, trying to figure out quantum mechanics. So now that we at least know this is consistent with the earlier description we were using, now we are going to use this as our starting point in introducing Schrödinger equation. So I haven't actually written down any equation yet. So I probably should tell you how I'm going to write down Schrödinger equation. This is the process Schrödinger actually went through. So historically, he was actually trying to come up with a relativistic wave equation first. Because by the time of when this came out, Einstein's theory of relativity was known, he didn't want to write down something that was wrong. So he was trying to write down something that described a relativistic particle. But he had ran into some difficulties, which I won't go into, but he ran into some difficulties, so he gave up on that front, and he focused on, okay, what's the non-relativistic wave equation that hopefully won't have the same issues that he had with the relativistic one. And his starting place was, well, I have energy and momentum. Or I don't know where he started. He could have said, I have energy and momentum. So once again, he's not really deriving anything, because this is the fundamental law. He's trying to guess at it. And one way of guessing at it is, all right, what relationship do I know that has to be, in some sense, be correct? One relationship that he knew that had to be, in some sense, correct was the expression for energy. So he knew that total mechanical energy, or energy, is equal to kinetic energy plus potential energy, right? So at least that has to be somehow true, even in this new brave world of quantum mechanics. So what has to be true is that, let me write it in this more suggestive version, that energy has to be equal to kinetic energy, or momentum squared over 2m, plus the potential energy, which I guess would be just potential energy. Potential energy, by definition, is an energy function of position alone, right? If it depends on other things, then it's not potential energy. So let me express potential energy as as a function of position alone. And this is so all of this is a classical expression. The quantum mechanical jump comes in that, well, I have operators for all of this. So I have energy operator, I have momentum operator, and there's actually a position operator, which I haven't told you, because in wave mechanics, the position operator, x hat, is just x. Just that. Which, I mean, it is distinct, but it's, so anyways. So this can be a relationship involving operators. Now, the one difficulty with that is, once again, these operators, mathematically, it's kind of difficult to get at what does this mean? Derivative operation? Like, it's not a function. So for this to become meaningful, this entire set of operators have to be acting on some kind of a wave function. That's where you get an actual equation, actual differential equation, that's going to be the wave equation. So that's the Schrödinger equation. Let me write it out so that you actually have an expression of Schrödinger equation. This is what your textbook would call time-dependent Schrödinger equation. And depending on the textbook, some books actually start out with a time-independent Schrödinger equation. But I'm doing it the way I do because when you see time-independent Schrödinger equation, it looks like something that's super hard to memorize. And it doesn't need to be that way. because really the only thing you have to memorize are these. And this is something you can guess at if you remember these. And if you know this, and you know this, then you can write down the entire time-dependent Schrödinger equation, and that's going to be related to the time-independent Schrödinger equation. So the time-dependent Schrödinger equation would be, let me write the right-hand side first. So it's this momentum operator acting on the function twice. So it would be, let me write down the function first. Psi as a function of x and t. This is going to be acting on this once. Let me write down one position derivative. And I'm saving this constant for now. And it's going to act on it one more time to measure, like, so it's like, you know, if you have algebraically, if you have this, you know, operator times this gives you this, then, you know, when you act on that with the same operator second time, then you are going to draw out one more factor of p, so you're going to get p squared, right? That's how you measure p squared. Good? So that's how I'm doing the measurement here. Act on with this operator twice, so I get the double position derivative. And I have to write down the coefficients that I've been saving. I have minus I squared, that's just minus. So I have minus h bar squared. So that's a momentum squared. I need to divide by 2m. Divide by 2m. Good? So this is the kinetic energy term. This plus the potential energy term. With this, so this is the thing about this x hat being the x itself. It's not a derivative. So all I need to, for this acting on or whatever, I just need to multiply. That's it. I'm done. So the potential energy operator acting on the wave function, and after you have acted on, this x now behaves like a variable instead of an operator. So that's the left-hand side, or the right-hand side here. That's equal to the energy operator acting on the wave function, or this. So IH bar, time derivative of the wave function. So this is what your textbook will call time-dependent Schrödinger equation. Once again, even though I'm giving a kind of an appearance of some kind of derivation, that's not what I'm doing. That's not what I'm claiming to be doing. Because this is the fundamental law. It's like, can you derive Newton's second law? It's like, no, that's your starting place. You cannot derive Newton's second law. This is like Newton's second law of quantum mechanics. You can guess at it by looking for consistencies, but I'm not really driving it. This is our starting point. I was just kind of guessing at it by requiring this to be consistent with something that we knew had to be true. So that's the time-dependent Schrödinger equation. Guess we are kind of due for a break. So we are looking back at the same picture, particle in a box, but so before we were approaching it intuitively, and we are going to get the same result, but this time using this fundamental, sort of Newton's second law of quantum mechanics. So, and you will see why I said that this is the simplest possible quantum mechanical scenario. So let me write down the Schrödinger equation, but applied to this specific situation. Schrödinger equation. So I guess I can start out with the full expression, and then I will cancel out whatever happens to be 0 or whatever. So full Schrödinger equation is this, minus h bar squared over 2m, double position derivative of this function, plus Vx psi x is equal to I h bar single time derivative of psi. Right? That's the Schrödinger equation. Now, so this thing that I drew in blue, this is my v as a function of position. That's why I drew it, because I knew I would need it later. Does this v have a convenient kind of an analytically nice expression for this v of x? Like if I told you to express this potential energy as a function of position, how would you have to express it?
Dirac delta function.
No, I'm not doing Dirac delta function. In fact, after today, I won't even mention Dirac delta function because it's not a real function and it's an upper division material. But like, how would you, if somebody told you, write down a mathematical equation for v of x, how would you do that? Let me ask you this question. If I said v of x is equal to 0, am I right? Am I entirely wrong? Okay, how am I partially right?
It's only 0 in between.
All right, so I can say it's 0 for x between 0 and L. All right, so I know v for one regional space. How do I describe v here or here? What is the value of potential energy at this point, beyond x equals 0? Somebody said infinity, right? Okay, yeah, infinity. So for x less than 0, it's going to be infinity, or I can say it approaches infinity. What about x greater than L? Also infinity or approaches infinity. I don't know, I have trouble saying something is equal to infinity. So this is how you have to describe your potential energy. You have to, this is using piecewise function, right? Well, that's the only way you can describe the potential function because it's a piecewise function. It actually has discontinuities. It's 0 from here to here, and at x equals 0, it discontinuously jumps to some value. So it's physically kind of artificial. That's why I was saying infinite electric field, because that's the only way you can get a discontinuous electric potential. So it's a bit artificial, not really physically, but we are using this as a model. Now, recognizing that this potential is a piecewise function kind of gives you an approach to how you should write down Schrödinger equation. And so for this particular case, this doesn't end up mattering too much, but it is going to for a different example we'll look at later. So the approach we should take this entire space and divide it into regions. Regions 1, 2, and 3. It's kind of something you have been doing since physics 4a. When you have something happening discontinuously, like in a kinematics problem, acceleration suddenly changing from one constant value to another constant value, then you break it up into parts and do it in parts, right? It's the same thing here. I broke up it into regions. And you can write down Schrödinger equation for this region, Schrödinger equation for this region, Schrödinger equation for this region, right? Now, this is what I want you to imagine. I'm not actually going to write it down, but just imagine. Do you envision any problem imagining writing down Schrödinger equation for region 1? Like, will any of these terms give you a problem? You have infinite potential. So that means you have infinite term here. So this is actually the justification for saying that psi at x less than 0 is absolutely equal to 0. Because if I have something that's approaching infinity and something that's 0, I can say that's 0. 0 times whatever is arbitrarily large is still 0. So in this region, that's where, so before when we are going through intuitively, we just say intuitively it should be 0 here. Now we have a mathematical justification. the only way Schrödinger equation can come out reasonably with this infinite potential is if we say the wave function here is 0. That's the only allowed value of wave function. And with that, the Schrödinger equation kind of becomes silly. It just says 0 is equal to 0. Yeah, I guess that is correct. 0 is equal to 0, but we don't really need to write that down to know that. Good? The same thing happens in this region, right? So psi of x greater than L, this also has to be 0. Right? This potential is infinite, so I really want this term not to explode on me. So the only way to make sure that this term won't explode on me is to kill it with a 0. Okay? So this is actually why this is kind of a nice, simple picture for quantum mechanics, because we can say that for this infinite region of space, we don't have to do any kind of solution or solving anything because it's just going to be 0. Wave function will be 0. We only have to describe the wave function within this limited space. So that makes things kind of easy for us. We just have to, whatever expression come up with, whatever solution we come up with, we just have to make sure that it works in this limited space. Okay, so really the one region that where we actually need to describe stuff is region 2. And so let's try to write down Schrödinger equation for this region 2. So let me do that here. I need a little more space. I think you guys all know what v of x is now. So Schrödinger equation. So I'm going to use subscript 2 as a reminder that this is the subset of this equation that only applies to this region. So minus h bar squared over 2m. I guess these are all constants. I'm not going to change any of this. Partial derivative of the Schrödinger, the wave function in region 2 with respect to x plus, what is this in region 2? Yeah, 0. This time for a different reason. This time the potential is 0. The wave function is hopefully not 0. So in other way, the term itself is 0. That's equal to I h bar partial derivative of the wave function in region 2 with respect to time t. So this is the Schrödinger equation in our in this region. And I can actually tell you what the solution to this is. And this is kind of a dirty trick that's very common with the physics. So have you seen a differential equation that looks like this before? If you're thinking wave equation, this is not exactly it, because it's a double position derivative equal to a single time derivative. So you haven't really seen it, right? So, so this is a new differential equation that most people here haven't seen before, haven't solved before, haven't pretended to solve it before, right? And the truth here is that even as much as I pretend that Math 3F is a core requisite for this class, it's not. And even if it were core requisite, like that doesn't mean you passed it. You might have enrolled in it and then decide to drop out of Math 3F, right? So in this class, we are not really going to, like the moment I start saying inhomogeneous linear equation, I'm doing something wrong. So we are solving differential equation, but solving in the sense that physicists do it. We're just guessing a solution to it, and the solution we guess just conveniently happens to work. So let me tell you the dirty trick in physics. We have a very convenient guess. We are going to guess every single time as a solution to a differential equation. Doesn't mean it always works, but it works like more than half the time, even in upper division. This is our universal guess for differential equations. Our universal guess is of the wave solution. It's actually, it kind of takes form of the plane wave. So wave of xt as a function of position and time, is some kind of complex exponential. That's our guess. And I guess this combination here, the combination that goes in here is the function of position and time. And it's a function going into complex exponential. Might as well form it in the form kx minus omega t. So that's our guess. Let's see if this actually is a solution to this. It might be, might not be. That's the whole idea of guessing. We don't know if it is, but this is so often actually the solution. It might be. So let me give it a try, and whatever we get, we get. Everyone good with that? Okay. So let me plug it in. See what I get on the left-hand side. I get so minus h bar squared over 2m minus h bar squared over 2m. Let me write it down. So this is our guess, and this is our record of the trial, how the guess works out. So double position derivative. This is sort of why we are guessing on exponential. It makes our calculus super easy. We don't have to do anything. All we have to do is pretend to apply chain rule, by which I mean these factors come out. So the double position derivative, it really means taking out this factor of ik once, twice. Now I'm done. Okay? All right. And then I still have the original function left. So let me write that down. Psi of xt. Okay? Plus 0 is equal to the right-hand side. I h bar single time derivative of this. Once again, the exponential makes calculus easy. Nothing changes here. All I get is this factor to come out. So minus I omega. And then I get the same function back again. So psi of xt. All right, so I see something that's promising. This is the nice thing about guessing on exponential. The functions are kind of guaranteed to cancel out each time because none of the derivatives you did changed anything, right? So all I get are these coefficients that remain, which are minus, so I squared is minus 1. So minus 1 times minus 1 plus 1. H bar squared k squared over 2m is equal to I times minus I is 1. So h bar omega. Does this sound reasonable? Like that this combination of coefficients, quantities, wave number should equal this combination of h bar and omega. Let me rewrite this in a way to convince you. H bar times k, I guess I erased it. That was h over lambda, right? So h over lambda, that's my momentum p. So, so the left-hand side, all that's saying is momentum squared over 2m. And the right-hand side is that's saying that's equal to E. A or H times F. So kinetic energy is equal to energy. It's almost a kind of circular argument because like I knew that was the case. So I guess now something should be sound a little bit off in your intuition. If I'm simply telling you that yes, this guess is actually the solution to this differential equation. But do you feel like plane waves should represent what's going on in here? No, right? I mean, I have this barrier. Where is plane wave coming from? Like, I have this barrier. Where is plane wave going to? So, so what this is this is, you know what, I'm going to forget all the mathematical terms. It's kind of a solution, but you need to restrict it. So here's one way in which this is nothing like the solution that we are expecting it to be. So whatever solution that we are expecting here, we kind of want, this is what we want. We want psi or at x equals 0 at any time, we want this to be equal to 0, right? Now, when you look at this, you're not going to get that because you plug in x equals 0, you get psi of xt is equal to a times exponential of minus I omega t, meaning at different times, it's not going to be 0, it's going to be something else. And the same, you get the same problem at this end, right? So this technically satisfies this differential equation, but what it does not satisfy is, we call this boundary condition. It's kind of what it sounds like. This is a boundary, and I was saying that this is a condition that needs to be met at the boundary. We call it boundary condition. So this is a general solution which could kind of work as overall thing, but I need to find a specific case that that satisfies this boundary condition. And now here's a bit of a difficulty here. So if you try to fit this to that boundary condition, you say, all right, so at x equals 0, you want to impose this to be equal to 0. It actually doesn't work. Because if you want this entire expression to be equal to 0, the only way that will happen is if A is equal to 0, which means I don't have a wave, right? So this is where I have to tell you a bit of well, one nice mathematical factoid to know about differential equations, especially linear, is it homogeneous? Differential equations, linear differential equations, and two, something to be aware of these plane wave solutions. Especially in quantum mechanics, these plane wave solutions, they are always going to be unphysical. They will never represent something that is a physically existing thing. That's the nice thing about this particle in a wave. It represents something you can easily imagine existing physically. This plane wave, if you do it properly, what we would represent is it would represent this particle spread out all space and time, all space. Like that's, I mean, maybe that can happen, but that's so, unimaginably unphysical. That's what plane wave will always represent. So you need to be kind of wary of plane waves when you are dealing with quantum mechanics. But it can be a basis of how we build up our solution. So this is the factoid that's useful to know about differential equations. So this is a differential equation, right? Suppose you have two solutions. Let's say psi 1 and psi 2. Let's say they are both the solutions to this differential equation. From your math classes, do you know if their sum is also a solution?
We only know it for ordinary differential equation, but is it also true for partial?
We'll say this is well behaved enough that it's going to work. It's also another common assumption in physics that we are going to assume all our functions are well behaved. There's no pathologies in those functions. I don't know if it holds for partial differential equations in general. It holds for ours. Good. So the phrase is any linear combination of these, meaning it can be a scalar coefficient, another scalar coefficient. This is also a solution to the same differential equation. And you can, if you kind of go through it, you can see, each of these derivatives, it's split, you distribute it between these terms, and each of these terms are going to match the corresponding term on the other side, so it's going to work out. So that's the fact we are going to use. So I have this solution in, this traveling wave solution, that is a solution, And I have a sense that the kind of the solution that I want here is the standing wave solution, right? So what I'm going to do is I'm going to use two traveling wave solutions to build me a standing wave solution. So this was my guess number one. That didn't really work out. Even though all this worked out, when I started checking boundary condition, it didn't work. So now I move on to my guess number two, which is based on this. So my guess number two is this. So I'm going to use this as one of my guesses. So this is the rightward traveling wave, right? I'm going to add it to leftward traveling wave. So say, all right, now this time my guess for psi in region 2 is this, a exponential of I kx minus omega t plus add it to a wave that's traveling the other way of the same amplitude. A times e to the I. So if it's going the other way, it must be, I guess I can do it two different ways. Which one do I prefer? I do prefer this, minus kx minus omega t. Does everyone see that this wave is traveling to the left in the negative x direction? Yes, this is how you see it here. The way you see that this wave is traveling to the right is imagine what you need to do to x so that as you increase t, as time passes, if you have to move the point to the right or move it to the left to keep up with the same point on the wave. As t increases, x has to increase with it to keep on the same point on the wave. Here, you have to do the opposite. As t increases, x has to decrease so that this phase parameter doesn't change, meaning you are on the same point on the wave. Yeah? So, all right, so that's our second guess. And I guess before I plug it into here, actually, okay, I don't need to plug it in here because from this, I know that is a solution to this. Right? Now, what I need to kind of be sure of is that when I check the boundary condition, that it'll work. Right? Let me do a little bit of pre-simplification so that it's easier for us to see this. I'm going to, so I'm just go through a series of algebraic steps, follow it, and make sure it actually makes sense, that I didn't make any mistakes, and then we will deal with the end result. I'm going to factor out A. So I have A times, I'm going to write this out, e to the I kx, multiply it with e to the minus I omega t, plus, I factored out A, so it's e to the minus I kx times e to the minus I omega t, right? I see something else I can factor out, e to the minus I omega t. So I have A times e to the I kx plus e to the minus I kx times e to the minus I omega t. Does this look familiar to any people? Oh, I messed up. Did I mess up? I kind of messed up, which I'll need to fix later. I will go back and fix it later. So what does this look like? It looks like a cosine of kx, all right. So it's going to be, it's actually 2 cosine of kx. So it's 2a times cosine of kx times e to the minus I omega t. So this is where I'm recognizing that I messed up because at x equals 0, I want my wave function to be 0. But if this is cosine, this is 1 instead of 0. So I actually wanted a sign here. So I'm looking back here. If this was minus instead of plus, then I would have sine, right? Or something that's related to a sign. So for this to be minus, this should be minus. So this should be minus. And like this plus being minus is actually no problem in terms of our guess, right? we could have guessed the psi 1 minus psi 2. So let me fix that. So this is minus, meaning this is minus, meaning this is minus. So instead of having, so this is actually 2. So let me just write it down so that I'm sure I memorized the formula correctly. E to the I theta minus e to the minus I theta, that should be equal to, 2I times sine of theta. Right? Because this is the formula I'm remembering. Sine of theta can be expressed as e to the I theta minus e to the minus I theta over 2I. And when you expand this out using Euler's formula, 2I cancels out whatever's at the top, and you get sine theta. Right? Okay. So this here is equal to 2I sine theta. So you have 2I times A sine kx. So this is a solution that will now meet our criteria. So this meets the boundary condition here. When you plug in x equals 0 here, sine of kx is 0. So no matter what these are, it will be 0. Good? Now we have boundary condition at the other end. We have this condition that psi of x equals L, it should also be equal to 0 at all time, at all moments in time. So what the other thing we need is, so let me just write down the equation and see if there's a condition we can impose. If we write that down, psi of 2, x equals L, t, we want this to be equal to 0. Then plugging in x equals L, then what we have is 2I times A times sine of Lx times e to the I minus I omega t. So what this condition means is that, well, this is the only free parameter I have, so this must be equal to 0. So I guess L times x must be a multiple of pi, I think, and pi. Right? If it's 0, pi, and then 0, pi, 2 pi, 3 pi, it's going to be 0, right? Okay, so, wait, sorry, I plugged it in wrong, sorry. Not L. Sorry, it should have been KL. Sorry, I don't know why. I plugged in L for K, not L for X. So plugging in L for X, it's KL. So what that means is, sorry, let's stop here. So K times L is equal to n pi. Okay, so K is 2 pi over lambda, right? Okay, so 2 pi over lambda. So when you solve for lambda, move lambda over there, move n pi over here. Pi's cancel out, so you get 2. So you end up with lambda is equal to 2 pi L divided by n pi, or 2L over n, which is the result we had before. So this result we had before, that there's only a limited kinds of wavelengths that are allowed, we get that result by applying this boundary condition to the solution to the Schrödinger equation. So all these results that we can intuitively get set, you can also derive them mathematically rigorously once you have Schrödinger equation. So for this particle in a box, particle in an infinite walled box, all this kind of looks, so all this machinery we are using seems excessive. Right? Like, why were we doing that? We had the answer like 2 hours ago. 2 hours later, we don't have anything better. We're just reconfirming the same answer. It's because, it's like what we are doing here. It's like a small screwdriver. And this is power tool. And there are tasks that small screwdriver will do that power tools can also do. But there are tasks that require power tool. So probably not today. I only have 12 minutes left. Another set of quantum mechanical problems that I think are solvable at our level is what's called a finite square well. This is a more physically reasonable version of the infinite square well. So here we said the potential goes to infinity. What if the potential doesn't go to infinity? Instead, potential tops out here, and then it becomes flat. Potential tops out here, then it becomes flat. So this is something that's physically reasonable. As in, okay, so you have discontinuity in the potential, but like you can have that potential wall. And to analyze this, our intuitive approach won't work anymore because there's some probability that particle will be here, even if it doesn't have enough energy to actually present here. We'll talk about that later. So that's where you do need a Schrödinger equation, because you need to. So one of the form of the solution that'll look like is something that looks like this, for example. And we need, it's a continuous function. And we need a set of differential equations that will describe this continuous function, continuous smooth function. So we'll get to that sometime soon. I'm not sure exactly when. But that's the reason we have this Schrödinger equation. And in this semester, we won't use it as much. That's because it does involve a lot of difficult calculus and algebra. A lot of that is left to your upper division quantum mechanics or upper division level work. But what I want you to kind of point out while we had the form of a solution here is some of the things that kind of useful to have a motivating kind of introduction. So one of the things you will see in your textbook somewhere is something called the time-independent Schrödinger equation. So this is a time-dependent Schrödinger equation because it's a partial derivatives as a function with respect to position and time. The time-independent Schrödinger equation is a Schrödinger equation that describes a subset of solutions here that's called stationary states or states that don't vary with the time. And let me write down what that equation looks like so that I have some place to get to. And I'm not really going to drive it because that's probably more upper division thing. You talk about separable solutions and whatnot. I will just point to things without writing them down. So this is the time-independent Schrödinger equation. Minus h bar squared over 2m. And now I use lowercase psi, which will only be a function of position. That's the time-independent portion. And that's going to be an ordinary derivative with respect to x, double still, plus vx times the same time-independent wave function is equal to E, just the energy number, not an operator. Just the number times psi of x. And there's a lot about mathematical properties of this stationary state that I won't get into. But what I have written down here, this is a stationary state. You might ask, how is that stationary? I have it as a function of time. So this is the thing about stationary state. It's not that it doesn't have any dependence on time. It always has this fixed dependence on time. So this is so-called stationary state. It's actually a part of the, there's a full wave function, but you can always write down the full wave function this way. It's this full wave function. Once again, this is only for stationary states, no other state. For stationary states, you can say that this is whatever the position wave function times, and the time dependence is always in this predictable way, e to the minus I omega t. And if there's time later in the week or if there's time, we might be able to go into in what sense it is stationary. We'll probably do that on Thursday, actually. So this is the time-independent Schrödinger equation. And the way it comes about is you assume that your wave function is a stationary state. Then this is the nice thing that happens. When you evaluate the right-hand side, all you get is h bar times omega, always. So you can say h bar omega is energy. That's where that E comes from. And on the left-hand side, you have the e to the minus I omega t that remains here. That just canceled out in every term. So when you have done that, that's how you end up with the time-independent Schrödinger equation. And in fact, what we call energy eigenstate, this is an example of this is energy eigenvalue. This is one of the allowed energies. And the states that have these energies are the energy eigenstates. Those are the stationary states. So what's called the stationary state are the states with a definite value of energy. Yeah. So let's see, what else did I need to go over? I guess 5 minutes. I don't know if I can do it justice. So here's an elephant in the room that I have mentioned briefly but didn't quite address. What does this stand for? Like, what is it wave of? Like, what is oscillating? I mean, something is oscillating, like something is doing the interfering and giving us these standing waves. But, like, is it, I don't know, it is some kind of, let's see. Is there something within this box that could serve as a medium? All right. If you imagine building this experiment with the electric field, this could be for a vacuum chamber. There's nothing in there except for this one charged particle that's been confined by the electric field. So
I remember you talking about the actual mass of the particle itself could be the one that's oscillating.
all right. So you are saying that the particle itself is the medium. So if it's the medium, the particle itself must be spread out all over, right? So this is the confusing, unintuitive, paradoxical part of quantum mechanics. Let's just say that you somehow prepare your particle in this state. So I'm just going to give you the experimental facts because these are what's not controversial. These are what I can tell you is true without any, any caveat or any kind of hedging. So if I have this box, and let's say I have prepared my particle in a state that can be represented by this wave function. This is my psi of x, and somehow my particle is prepared in this, in this state. And if our view is that what this wave function represents is this particle kind of smeared out all over, then we could say, oh, so this particle is literally smeared out. There's some part of the particle here, some part of the particle here. So now you try to do this. You try to actually measure the position of the particle. So you shine some light on it, or you try to measure the position of the particle. Then when you actually detect the particle, what you would see is that you would see the particle at one particular location. The particle itself is not spread out. You don't see a kind of a smear of the particle over the entire space. You see it at one location. But here's the kind of confusing thing. So you prepare the particle in the exact same state. You do the exact same experiment. And then next time, you actually detect a particle here. You do the exact same experiment again. Now you detect it here. Do it again. Now you detect it here. So, but this is this is what you see. Each time you detect a particle, the particle is definitely at one place. It's not actually spread out. So what this wave is made of, I'm going to have to leave it as a mystery. It's not the particle itself being spread out. The particle is one, it's like, think of an electron. I know in chemistry you guys talk about electron cloud, but even in electron cloud, electron is not literally spread out in the cloud. It's not, that's not the correct picture. But so imagine doing this experiment thousands of times. Then this is actually what you would see. I'm gonna just build up a kind of a histogram. So histogram kind of looks, I don't know. I'm not doing this well. Let me just draw out what the histogram looks like. Something like this. I don't know. Sorry, I'm not drawing my histogram well. What you're counting is, so for each kind of a bin, each kind of location, how many times have you seen the particle there? So you do notice that you do see the particle most here and here. And do you see anything else? Yeah, you never see particle here or here or here. There are the nodes where the particle is never present. So this is one thing I can tell you. If you have this wave function, then this is what we call probability density of the particle. So the probability density, and we'll discuss a little bit more later what we mean by probability density. But that's kind of what's represented by histogram here. The probability density is given by the absolute squared of the wave function, which to be technical is this. It's the complex conjugate of the wave function times itself. That's what always absolute squared means. So this is the interpretation of wave function. So whatever else the wave function represents, this is correct. So, and now to make it actually probability density, we have to do something called the normalization, as in, yeah, so we'll talk about that later, but at a minimum, what you can say is that where this absolute value squared is greatest is where you have greatest likelihood of finding that particle there. That's why you have greatest likelihood of finding the particle here and here. It doesn't matter that it's negative because all you care about is the absolute value squared. So that's one of the things about the wave functions that people somehow correctly guessed at. And this property will be important in doing other calculations like so calculations with the wave function, measuring the average momentum, average energy, average position of something. So let me point out one thing. So if you have a particle spread out like this, where would you say the average position of the particle is? In the middle. This is the average particle, right? This is my x average. Is the particle ever found at its average position? Yeah, it's not. It's just something. But this is not surprising to anyone, right? When you have a specific distribution of the particle probability, then like sometimes you get that average position, you never have that. You can do get the same thing with the energy. So yeah, so all right, I don't think that's all that surprising.